So I'll just record the in-class part. I'm not gonna record whatever we talk about in the sample final. All right, just to be clear. So let's go to the in-class first, virtual memory. The first question, by the way, feel free to check. So we have in-class slot, right? It should be 3 points for you guys. So either look at the video or look at what you have right now, download the PDF, just write whatever we put in here. So assume that you have 32-bit byte addressable, right? So 10. Do I need to zoom in? Let me zoom in once. Is it big enough for you guys? All right. So, okay, perfect. Sorry, I also have to have the chat windows open, so it's kind of like everything is in the way. We have 32-bit byte addressable. What does byte addressable mean? Basically, it means that I can go and reach to any single byte from my address. I use 4 megabyte page. Notice something different. We don't use 4 kilobyte page. So we have 4 megabyte page size, one level page table. How many bits? And Dropbox is full. All right. How many bits do I need for the page offset? How do I get that? How many bits do I need for the page offset? How do I get that number? Log of 4 megabyte. And what is that result? So I'll tell you some trick. Log of 4 plus log, something we learned in high school. Log of 1024 plus log of 1024. This is 10, this is 10, this is 2. So that's 22 bits. 22 bits. So if you got 21 bits, you might get confused with 2 megabyte page size, which is another really common page size if you choose to use what we call huge page. In that case, the page offset would be 21 bits. In this case, just my weird configuration, specifically for the exam, right? I might do the same thing again for your final exam. I'll just have some configuration. As long as you understand the fundamental behind these concepts, you should be able to tell what is what, right? Assuming that the index bits for each level is in the page table and they are divided equally, what's the maximum number of page table entry per page table? So the first part is a trick thing that I put in here. I only have one level. So what would be the index bit am I having here? How many bits do I have left? Do I have to divide again many other level? I have only one level page table, so my index bit is 10 bits, right? If I have 10 bits index bit, each bit can represent an entry. So the combination of 10 bits, how many different rows can I have on my page table? How many page table entry can I have? Think page table entry, think that row that I draw earlier. So how many row if I have 10 bits to 2 to the 10, right? By the way, for your answer, feel free to just put in 2 to the 10. You don't have to actually do the math out. That's fine. That's fine by me. Ideally, you can just do a quick, simple 2 to the 10 is always an easy one. It's 1024. 2 to the 20 is million. The way I think about it, kilobytes or kilo is 2 to the 10. Mega is 2 to the 20, right? So this 2 to the 10 multiplied by 2 to the 10 again, you get about 1 million. It's a few more, but it's roughly about 1 million. With all the above assumption, what's the maximum number of physical memory in the system that I can support? What can be the maximum size of my DRAM that I can plug in? And then I can be able to, I can tell like that address goes there, that address goes there. If my page table is only have 1024 entry, I have 1024 entries. I have, yeah, how much is that? 1024 multiplied by 4 megabytes, right? That's basically 4 gigabytes. Remember the old day where we have 32-bit CPU and it actually can only reach to 4 gigabyte? Like, it makes sense during the time. You don't have a lot of memory. You would be like you would have a fancy machine if you have 2 gigabyte of memory. Back in the day, right? One of the reason why you want to have like a 64-bit machine is that now you can have the address that span such a long range of number, right? So the last thing should be pretty simple, but again, it can be tricky if you think about it, not being careful about it. What's the maximum capacity needed for me to support the page table? So the page table is that row thing, right? So how many rows am I having here? How many rows do I have for my page table? 1024, right? What's the size of each row? How many bytes is that? What's the size of each row? 4 bytes? 4 bytes, because it's 32-bit byte addressable means that 32 bits, 4 bytes. So 1024 multiplied by 4 bytes, right? That's all for the first part. Now, here's the tricky part. I'm gonna give you some time to think about it. I'm gonna give you some time to think about it. So let's do this together. Let's do this together. I'll explain the question first. The first thing I have is like, okay, gotcha. Question doesn't matter if you answer in bytes or bit. No, it doesn't matter. I can do the division by 8. It doesn't matter. Really. Like, even though I said like answer in bytes and you answer in bits, I would just like maybe dock like 0.5 points from your answer or something. But if I didn't say anything about that, just answer in bits is fine too. So let's create a much simpler machine. They use big endian. Okay, that's one keyword, big endian, right? That can have something to do with this, whatever table that you look at down there. It utilizes 4 megabyte page size, 32-bit address. 32-bit address basically means that each address location is 4 bytes. Assuming that the following data in the memory, so these are in hex. Whatever number you see is a hexadecimal number. The left side is the lowest bits. So the left side is like the lowest byte. So this is the first part that I got like the assignment a little bit wrong. This is lowest byte. That's where the Discord session comes into play. If you this is something that looks wrong to you, double check with me because I'm human. I can make mistake. I can make mistakes, and if I make this mistake, which by the way is embarrassing, but I should be able to admit fault, right? It's wrong, right? Simply it's that. The page table root is at 0. It basically means that if I look at my table, this is my page table, right? It starts at address 0 and it goes from there. It goes from there. So how many bytes does the first row take? So the first row is start at byte 0. Where should the second row be? What byte is that? Right. How big is one row here? What's my page table entry size? How big is one row? 32-bit, right? Because I just said page table entry is 32-bit long right here. Page table entry is 32-bit long. So this is going to be 32-bit. The next row will start at byte number 4. The row afterward will start at byte number 8, 12, 16, 20, 24, 28, so on and so forth, right? Each row is basically 32 bits or 4 bytes. Also, quick note, it just happened that if you look at this table, right? So let me use whatever, some color here. This, it just happened this is 1 byte. Anyone know why two-digit hexadecimal number is exactly 1 byte? How many bits is two-digit hexadecimal number? It's 8 bits, so that's 1 byte. So if I think about it that way, right, then if you look at 4 byte range, right, this thing is going to become my page table entry. Because I said this table, the roots of my page table start at 0. So address 0, that's my first row in the page table. Then the next group of 4 bytes is going to be the next row, right? So this thing goes here. This thing now goes in this row. This is actually the content in this row. Now I just basically visualize this for you. All right. Now you see the table. Now you see also the entry, right? And what I say is the most significant bits here, the most significant bits are used for the physical page number. What I'm saying is if I happen to zoom into this entry, so let me use a different ink color, I guess pink. This, if I happen to zoom into this, 32 bits. E, right? The left part will be used for physical page number, and I did not tell you how many bits is that. I did not tell you how many bits is that. All right. But you can guess from the number of bits used in the page offset. All right. So we will get to that in a bit. We'll get to that in a bit. But the question asked for here. All right, give me some color. Let's, no, I don't want to use black because that's the question color. Let's use the green. If I have virtual address, dead beef was my physical address. It's as simple as that. My virtual address is D E A D B E F. Do we have first? The question spans into two things. Do we have enough information from the given table and everything else? And if we have enough information, what's the physical address? All right. So we'll leave you at this for now. I'll have you look at the table. So let me zoom in one more time, just in case it's better. Here, wait a second. All right. So from here, I'll give you 10 minutes. We can talk and we can chat. All right. And we will go through this after. Well, I'll leave the time for you first. And I'll give you an extra credit for the first person who got the answer. How about this? For the first person who answered on the chat, you get 0.5% of your entire grade. That's quite a lot, actually. I think that's kind of like 5 points in the assignment or something like that. For the first person who got the answer for this question. All right. We'll be back in 10 minutes. And then we'll go with the how do we solve this. All right. First to answer correctly get 0.5%, like flat 0.5% on your grade. Okay. All right. Now I'm giving you 10 minutes, so we'll come back at 2:52. We'll be back at 2:52. Feel free to ask question as well. So question on the chat is fair game. Whatever allows you to make progress on the question is good. All right. So what is the answer? I told you I am waiting for you to go through it first. And if the 10 minutes window expire, I'll come back and we go through that question. But please try, because the first one to answer correctly, you get extra credit on your grade. Okay, you got it. You got it. So now, Jordan, you got it. You got it. That's really fast. Yes. Thank you. Okay, so let me remove the 10 minutes. I cut it. Yes, that's really quick. I'll cut it to 2 minutes to look at the answer, and then I'll come back and explain. I just need to make some espresso. Sorry. I just need some energy for myself as well. That's kind of like what I'm trying to get at here. So give me 2 minutes. I'll be back with my coffee. But in the meantime, please look at what John said on the chat, right? We don't have enough information because what that bit tells me is way outside of the table. It's really not that hard. This first question is actually not hard at all. If you know what to do to get the virtual page number. The key here is once you have the virtual page number, you figure out that way out of this table and there's not enough information. All right, I'll be right back. I just need to get coffee. Hey, I'm back. All right, so let's break this down together. Dead beef. I have, what's the page size? 4 megabytes, right? 4 megabyte page size, so that's one keyword. 4 megabyte page size. This means that I have 22 bits for the page offset, right? I have 22 bits for the page offset. This is bits 0 to 3, bits 4 to 7. So the first 4 bit, each one of these is 4 bit, 4 bit, 4 bit, 4 bits. That's 20 bits. What you have is D. What's D in binary? What's D in binary? 1101. Thank you. 1110. A is 10, so 10 is 1010. We need 2 more bits because over here this whole range is 20 bits. We need 2 more bits from this part, so your virtual, your VPN is what? Virtual page number is going to be, so arrange, let me use the arrange, VPN is these bits, right? So that's 1101, 1110, and 10. That number turns out to be, I would believe John, 3560. So you're looking at 3560 entry on your table. But if you look at this table up here, right? How many entries do I have per row? I can have 4 entries, right? Per row. Oh, thank you. All right. Thanks for the correction. I just totally trust you. Because I mean there's an actually, so there's 890. There's an actual easy way to figure out. Definitely not on this table because each row, right, is four entries. How many rows do I have? I start at 0, 0. I end at F0. So we definitely have 16 row. We have 16 row. And you have 4 entries per row. So in this table, we only cover the first 64 entries. It covered the first 64 entries, right? You want the 890 entries is definitely not on the table. So we don't have enough information. Wait, 1101, 1110, and 10. 110, 11. Yeah, it's the same thing. It's the same thing. If you look at my writing and have a different number, you need coffee. Solution to everything. All right. So now let's go to the next question. What about when I have the virtual address? My virtual address is 0 F F F F F F. All right. Same deal. I'll wait until someone answers. Whoever answers first got the extra credit. Let me double check the table. This one should have an address. Look at this table and tell me what is the physical address. Again, I'll put it here. I'll put the address, the virtual address here. Virtual address is 0 F F F. For the second question. Let me know what's the answer. All right. Answer. Wait. Virtual address. It should it should have 32 bits. So quick hint is it should have 32 bits. Oh, great question. Great question. From the address point of view, the number I put in here, it doesn't like basically the left side is the most significant bits, the right side is the least significant bits. Definitely enough information. And you are almost there. Robert, you're almost there. You're almost there. That's that's the entry you want. Yeah, you need to get something from the entry and you need to do something with offset. The resulting address should be 32 bits. So Robert, you're almost there. You just forgot your page offset. It's like not there. That's such a long pause. Why is there such a long pause here? It's almost, you guys are almost done. Or should I just go with the cover the solution? All right, some quick thing so that we can retrace the steps, right? 4 byte, 4 byte, 4 byte, 4 byte, two more bits from here. Quick thing. So basically, physical address, right? PA have to be PPN and the page offset, right? Page offset from here, you will notice it's a bunch of F. So the page offset part has to be 1 1. It's basically right. So that's the first 20 bits, and we need 2 more bits. So this is in hex. This is in binary, so to reduce confusion. So your address should end with a bunch of F. So if it's not a bunch of F, there might be something off here. So now the question is, what's physical page number? The reason why I said you're almost there, because if you look at this part, right, it's 0 0 0 0 1 1 1 1 1 1 1 1. This is what goes into the page offset, and this will be going to the virtual page number. It turns out to be number 63. Entry that corresponds to 63 is this entry, 6B124B31. Page table entry is 6B124B31. How many bits am I taking? Because I use a 32-bit addressing machine that has a 4 GB DRAM. So how many bits am I taking from this entry? If I say I just take the most significant, like starting from the most significant bit, and from there, I'll take whatever bits I need and I'll plug page offset to that. So how many bits am I taking? Don't forget page offset right now is 22 bits. So PPN is going to be 10 bits. Starting from here to here, starting from left to right. So you take 6 and B, those are 8 bits. 1 is 0 0 0 1, right? So it's 6B 0 0, and then we start from here, right? 0 0 1 1, the rest are F F F F F. This is essential, this is binary, right? This is essentially number 3. So it's 6B 3F F F F F. Our physical address. Oh, how do I get the PT? Yes, for sure. So I have the virtual address, right? Here. And from my virtual address, I can tell from just getting the correct bits that my virtual page number will be the uppermost 10 bits. What's the uppermost 10 bits from this virtual address? 0, F, and then the 2 more bits, right? 0 is 0 0 0 0. F is 1 1 1 1, and I need 2 more bits from the next letter. The next letter is F, so it's guaranteed the next 2 bits is going to be 1 1. So my virtual page number is basically 0 0 0 0 1 1 1 1 1 1. This is 63. All right, with me so far? All right, so we know that from here, from address 0, what we need to do is to go to the 64th, right? Because we start at address 63. So it's going to be whatever entries goes in here that would correspond to index 63, which is the 64th entry. And we happen to know 1 row is 4 entry. We have 16 rows, so we definitely know 64th entry is the last guy here, right? Are you with me so far? Basically, it's just if you count like 0, 1, 2, 3, 4, 5, 6, 7, 8, you will actually go. This is basically VPN 63. You just go to that 4 bytes. So that's my page table entry. So, and as I said in class, right, the page table entry consists of two things. Page table entry consists of two things. This thing here actually can be broken down into physical page number, right? One part is physical page number and the other is status bit. And in the question, I just happen to say the physical page number will be from the leftmost and count down from it. And we need, because our address is 32 bits, right? Page offset is 22 bits already, so we have 10 more bits. Those 10 bits going to be coming from the PPN, so that's 6B and 00, right? 6B and 00, and then you plug the rest are just from the page offset. So is it more clear now? All right, awesome. So I will stop the recording right now. Stop.